Hi, this video is on the magnetic forces that magnetic fields exert on charges and wires. We've been saying for a while now that the electromagnetic force, although we've been taking them separately, cannot be broken down any further. That it's like the gravitational force, that you can describe its properties, but you can't really break it down and prove it mathematically. And so this is a good example of this idea, that for magnetism we find from experiments that a magnetic field characterized by B exerts a magnetic force, we'll call it Fm, on a charge Q only when the charge is moving relative to the field. So again, this is just something that we see from experiments, and that force is given by this guy here. So the magnetic force on a charged particle is equal to the charge of that particle times the velocity u of the particle cross with the magnetic flux density B, like this. That's pretty interesting. We've been talking about these cross products, and maybe you don't think that there are any applications to these cross products. Well, if you thought that way, you would be wrong, because this is something that we just see in nature. U cross B and then times Q is the force on a charged particle in a magnetic field. So it's the goal right now, the immediate goal, to understand this equation. Now, remember also that the electric force of a charge in an electric field is given by this. And so, remember, electric field was newtons per coulomb, so if you multiplied by coulombs, you get newtons. The total force in an electromagnetic field would be Q E plus U cross B, like that. This is called the Lorentz force. But for right now, it's our immediate goal just to understand the magnetic force here, this guy, or in the Lorentz equation, just this guy. Now let's understand the direction of the force. So remember that when you perform a cross product, the resultant vector has a direction that is perpendicular to both of your vectors. So in this case, if we have a velocity vector, u, and a magnetic flux density vector, b, then the force is going to be perpendicular to both u and b. So suppose we have a magnetic field going into the page like this. Remember, we represent vectors going into the page with circles with x's in them, like it's a vector tail that you see. Okay, here is our magnetic field, B. And let us also suppose we have a charge in this magnetic field. Here's my charge. And we're gonna say that it's positive for right now, plus Q. And suppose that it's moving up. It has a velocity up. Here's vector u. And we ask ourselves then, in which direction would the force of this thing be? Well, we can answer that with the cross product, with the right hand rule. So take your right hand, point your fingers in the direction of the first vector, so that would be up. Curl your fingers towards the direction of the second vector, which would be into the page. So if you've done that correctly, your thumb is pointing in the direction of the resultant, and your thumb should be pointing to the left. Again, fingers go up in your right hand, curl into the page, your thumb is pointing to the left. So that's the direction of the magnetic force this way, Fm. So that's interesting then, because the particle was moving up, then it's going to be accelerated to the left. So what does that do to its motion? Well, that's gonna move it to the left, but then its velocity changes. Then its velocity is no longer up, and then what you're going to see is kind of something like this. It was going up, and then force makes it go that way, and then so because its velocity changes, then the force will make it go this way, and this way, and this way, and this way. And so what this does is it makes the particle go in a counterclockwise, in this case, circle. Very interesting. Now, we assumed that the charge was positive. If we assumed negative, then we would just multiply everything we said, by a -1, the force by a -1. And so in that case, the magnetic force would point to the right, and this thing would be going in a clockwise circle. Very cool. Now, let's extend this idea to current carrying wires. Are there forces on a wire that is in a magnetic field? And what do you think allows us to make the jump from moving charges to current carrying wires? Well, remember that a current is a moving charge, or it is a bunch of moving charges. So suppose that we have a wire element, dl, so just a very small segment of a wire, and it has a charge dq and current I. Then, based on what we just said from the magnetic force, the small differential, that is, magnetic force on, I'll emphasize on the wire, is given by dq, which is the charge, u cross b. Okay, and then if we manipulate this a little bit, we get dq, and then the velocity of the charge would be the change in its position, which would be along the wire, so dl, divided by the amount of time, dt, cross b. Okay, and then if I move the dt over here with the dq dt is current. So this would be I dl cross b. All right, so we have the small force due to, or the small force on dl due to b is given by this thing. What do we do then if we want the force on the entire wire? Yeah, you guessed it. You should know this. We need to integrate then across the entire wire L. Okay, that is the force on a wire in a magnetic field B. Again, on the wire. It's just like you were in physics. The force on the wire by the magnetic field B. Okay, well, remember that we can have also surface and volume currents, right? So we could alternatively write that the force on a surface, we would write K ds cross B, or the force on a volume would be the integral over the volume of J, the current density, dV cross B, like that. Okay, so that's kind of cool. That's kind of neat. Now, so let's put two ideas together now. We've previously have seen that a current produces a magnetic field, right? And now we just saw that a magnetic field creates a force on a current-carrying wire. Therefore, one current-carrying wire will exert a force on another current-carrying wire, and vice versa. So let's say we have a wire here, wire 1, that's carrying a current, so there's a voltage somewhere to make this possible, right? And then there's another wire, call this I2, I1, this is loop 2, wire 2. Okay, so again, we just saw that there's a force on a wire in a magnetic field, but what if that magnetic field is being created by another circuit, another current, right? So in this picture, I2 creates a magnetic field, and then I1 is in that magnetic field, so it feels a force. Similarly, or alternatively, I1 creates a magnetic field, and I2 is in that magnetic field, so it feels a force as well. It's kind of a neat thing there. So let's figure out, what that force would be. So we're going to just consider for right now the force on, again, emphasize on 1. So in this case it would be on 1 by 2. So let's consider a small little element there, dl1, and it's got IDL1 like that. Okay, and we'll consider a small little element here, IDL2. And of course, there is a vector. If we're considering the force on 1, then this is the vector. We want this direction. Okay, like that. So let's ask ourselves then, what is the force on this little dl1 here due to this little dl2? Well, that would be, and we would write it like this, we'll call it 1, like that, but we'd write it df1. So this is on 1 comma m. And there are two d's there because we're considering two small segments right now. So this would be I1 dl1 cross the magnetic field produced by just this little piece, right? This is what we saw. That's this thing here. Okay, but from the Biot-Savart law, we know that what the magnetic field is that this thing is creating. From the Biot-Savart law, dB2 is mu0 I2 dl2 cross a unit vector in that direction divided by 4 pi r squared. And remember, this is not the original form of the Biot-Savart law. Remember that B is equal to mu0 h. The original form had an h in there. Now we're saying it's B, right? And so we need to bring mu0 into the picture. So now what we can do is we can say that the small little force, or the force on the small segment in loop 1 due to a small segment in loop 2 is equal to mu0 over 4 pi R21 squared times I1 dl1 cross I2 dl2 cross A R21, just by substituting that in there. dB2 goes right in there. And then finally, the force on, again, I want to emphasize this is on loop 1 by loop 2. So what do we need to do to get that total force now? Well, integrating once isn't enough because we've got two differentials there. We need to integrate once over I2, or the loop 2, to get the total magnetic field it creates. Then we need to integrate again over loop 1 to get the total force that it feels. And so we get that the force then, 1 comma m, is equal to mu 0. I1, I2 are constants. We can bring them out of the integration over 4 pi. Integrate over loop 1. Integrate over loop 2. And then we've got these cross products. Over r squared, like that. And if we wanted the force on 2 by 1, then we would flip the subscripts, right? And what you would see by applying some vector identities is that the force on 2 is equal and opposite to the force on 1, as we would expect from Newton's third law. All right, so let's worry about now kind of calculating those, or that integral, right? And let's look at some examples.